Good afternoon, and welcome to this month's SSE Community Discussion Hour. My name is Mark Urban Lorraine. I'm the Secretary of the Society for Scientific Exploration, and I'm pleased to be the host for this afternoon session featuring Mark Carlotto, who is an aerospace engineer with 40 years of experience in satellite imaging and related applications. Mark received his PhD in electrical engineering from Carnegie Mellon in 1981 and has written over 100 technical papers and 8 books. Outside of his occupation, his journey as an independent scientist has taken him to Mars and back again. Dr. Carlotto's first book, The Martian Enigmas, describes a 10-year-old investigation of the face and other unusual objects on Mars, using shape from shading and other techniques to analyze the 3D structure of the face. A second book, The Cladonia Controversy, steps back from the science of the Mars investigation and examines it within the context of the centuries-old search for life beyond Earth and its possible implications. His involvement in space-related investigations continues to the present and is described in Not of This World, an emerging picture of the UFO phenomenon. Dr. Carlotto's presentation today describes work related to his recent book, Before Atlantis, in which he applies Charles Hapgood's theory of Earth crustal displacement to the interpretation of ancient sites whose geometrical and astronomical alignments are not currently well understood. His blog and website, beforeatlantis.com, is frequently updated with his latest research, and I believe this also was a topic of a recent article that you published in the Journal of Scientific Exploration. So without ado, Mark's talk is pre-recorded. We'll play the recording, which will last a little over half an hour. And after the recording, Mark will be back and I will be hosting the Q&A session. So as the recording is going, use the Q&A button that it shows in the right-hand side of your screen to type in any questions that you have during the presentation, and we'll take them at the end. All right, thank you very much, and we'll start your recording.
Hello, everybody. I'd like to give a presentation on a paper that was published this past spring on a new theory of Earth crustal displacement. It's actually an old idea that in many ways goes back to the early 20th century, to Wegener's work in developing a theory of continental drift, which later became known as plate tectonic theory. His theory took many years to be verified. Actually, it wasn't until the 1960s. But in the meantime, others had suggested that besides continental drift, plate tectonics, there were other phenomena at work. Milanković had proposed the idea that there were changes taking place in the actual overall movement of the crust, which would result in changes in pole locations. And he believed that this worked together with plate tectonics to maintain the Earth in a state of equilibrium. And actually, we all, or those that are familiar with Charles Hapgood's work, his book, The Earth Shifting Crust, published in '58. If you realize that a few years before that, Morris Ewing and William Don, who were involved actually in some of the early work in proving Wegener's theory, seafloor spreading, and other evidence that took number of years to be developed. They actually proposed the theory of ice ages very similar to Hapgood's theory in '58. So rather than get bogged down in a lot of the history, and that's the ellipsis there, is to say there's been a lot of criticism of Hapgood's theory, and I'm not going to get into that here. What I'd like to do is present sort of the new version of this, and I think maybe it would be good after the talk, we could probably talk about some of the issues, some of the so-called problems with it, and how this new theory, some new ideas that I proposed in the spring may solve some of those problems. So Hapgood's theory is that basically boils down to, over the last 100,000 years, he proposed there were 3 previous locations of the North Pole. Shown here, see if the pointer works. There we go. Previous location was Hudson Bay, preceded by a location near Norway in the Norwegian Sea, and then prior to that in the Yukon Territory of Canada. And his hypothesis was based on climate data that seemed to indicate there was a correlation between glaciers and ice age events and different at different times, and he believed that these were correlated with shifts in the poles. So rather than the current theory, which is that there are global changes in temperature and other factors that cause ice ages, he believed that it was a local effect. So Hapgood's desire to, or his interest in the subject was really motivated by his interest and his curiosity about climate change. Mine was a little different. Back a number of years ago, I was planning a trip, and we're all familiar here. This is an overhead image of the Giza pyramids. And we're all familiar with their alignment to the cardinal directions, very accurately aligned, in fact. But I was going to Mexico, and I noticed a lot of the structures in Mexico are not cardinally aligned, and I wondered, why is this so? In doing a little bit of research, it appeared that others had noticed that there was a correlation in, for example, the direction of Teotihuacan in north of Mexico City and one of Hapgood's poles. In fact, it was very closely aligned to one of his poles. So here's Teotihuacan, here's the meridian going through the Avenue of the Dead. Here's other meridians from other sites. Here's Hapgood's pole shown here with the H, and these other sites, and this is something I'll go into in a bit. Using site alignments, I was actually able to refine Hapgood's pole and adjust it, find a location that was pretty close, and it turned out by making these adjustments, sites like Teotihuacan now appear to be aligned to previous locations of the pole. So I wrote this up and I submitted it to the journal, and I was all excited. And they said, wait a second, you need to sort of approach this more systematically. And it's so happy the peer review process is such a great process, because they said, basically you need to sort of take it a step at a time. First, show that there's an anomaly, and then within the context of that, present your theory as a solution to it. So the first step was to show that in analyzing sites across the world, archaeological sites, looking at their alignment, I initially thought, probably most sites are aligned in known directions, and there's only a few that sort of deviate. And if you look at here's some example sites. For example, Angkor Wat is aligned to the cardinal directions, like the Giza pyramids. Karnak is aligned to the solstices. The ziggurat of Ur in Mesopotamia is aligned to lunar standstills. And Kokher in Cambodia, I think it is aligned to zenith passage, sunrise directions. It turned out, I looked at about 224 sites, and most had explanations, but there was a significant number, more than a third, actually about 40%, that had no conventional explanation. So none of these explanations here we're looking at, and also considered stellar alignments to other sites, other geographical references, and so forth. But about 40% were unexplained. So the second paper, which was published, this was in 2020. The second paper, the first was published in the spring, which did the study, identify this possible anomaly. The second paper, published in the summer, presented this new model, which I call the shifted pole alignment model, which is The idea that rather than reference everything to the current pole, perhaps the ancients had referenced alignments, sites to previous locations of the North Pole. So in other words, different north had been in different directions. And showing some of the sites here on the left, these are meridians from sites that I had identified and correlated with 4 previous locations of the pole. One in Hudson Bay near Hapgood's original location, 2 others in Greenland and Norway, which kind of split his second pole, and then the other pole I moved from Yukon to the Bering Sea. And again, these refined alignments were based on, or these refined locations were based on looking at side alignments and correlating them, basically intersecting these great circles that you see here, doing this spherical trigonometry and figuring out where they intersected. So that was the second paper. And then, let me just also mention the fact that we're not just talking about cardinal alignments. I had noticed, here, or we noticed that, not all the sites aligned to the current pole are aligned cardinally, but a lot of them are aligned to the sun and the moon. So, similarly, if the poles were in a different location and the ancients followed similar practices, you can imagine that they aligned, way back when they aligned sites to the moon and sun, but the solstice and lunar standstill directions were different because they were referenced to a different pole location. So, working out all the math, and this is all described in these papers, explains how this is done. You come up with these alignment diagrams, and basically it allows you to determine, where these directions were during previous in previous eras where the North Pole was in, different hypothesized locations. Of course, none of this is proven. It's all hypothesis. So, with all that as a bit of a preliminary discussion, let me just go through the outline of the paper. I'm going to talk about global sea level, Milanković cycles, and linear prediction. This is this I think sort of is the essence for what the problem in climate models are, and I think where pole shifts fit in. Pole shifts being what I show here as possibly being the missing link. I then talk briefly about correlated events, Earth changes that have taken place that could suggest a possible mechanism. Hapgood proposed that it was a buildup of ice that caused crustal displacements, and Einstein, in the foreword to Hapgood's book, actually, he was of the opinion that it wasn't of sufficient mass. And in this paper, talk about here, we did a little analysis using crustal models and ice models to show, basically how ice would have affected the Earth's moments of inertia. And so I come up here with what I call Hapgood 2.0, which is a refined version of Hapgood's theory, which is based on actually proposing a completely different mechanism. And that's really I think the contribution of the paper. And I'll present some preliminary findings and summarize at the end. So let me press on. Milanković cycles are these cycles where incident solar radiation varies as a function of Earth's obliquity, its precession, the change in Earth's orbit around the sun, and other factors. And there's been an attempt to try to correlate these with measurements of ice or sea level. Sea level is really inversely related to the amount of ice, temperature, atmospheric oxygen, and other things. So, the basic idea right now in climate science is that the motion of the sun, moon, and Earth have something to do with defining these Milanković cycles that modulate the amount of solar radiation, incident solar radiation, and then this results in changes in global temperature, sea level, and polar ice. So that's the current theory. So global sea level is sort of the key proxy. as sea levels drop, polar ice increases and vice versa. And this is sea level data over the last 250,000 years. Now, if we start looking at sea level and other parameters, global parameters, and I won't go through all of them, but sort of hitting on the key one here, which is insolation, because this is what comes from Milanković theory. You notice that there seems to be some correlation there. I mean, in general, though, insolation does appear to lead sea level changes. And in some cases, they line right up. In other cases, they don't. In some cases, there's a correlation. In other cases, there's no correlation at all. But there's something going on there, some degree of correlation. So I thought, well, being an electrical engineer, I'm not a geologist or a climate scientist, let me look at the changes in sea level, which turn out to be highly correlated with insolation, and construct a linear predictor, which is here, which is basically estimating sea level change as a function of insolation. And then I just sum up the changes to give the estimate of global sea level. And so, so this is the estimated global sea level as a function of insolation here. And this is the actual global sea level. So it doesn't do a great job predicting it. Gets some of the undulations here, but there's a big discrepancy in level. If I subtract the two, you get this, which is very interesting. This could be interpreted as sort of two regimes here. One is a period from about 130,000 years ago to about 20,000 years ago, where sea levels are dropping and ice is accumulating. And then after the last global maximum, about 20,000 years ago, the ice begins to melt and sea levels rise. So again, this is the difference between global sea level and what's predicted by insolation. So this is what insolation does not predict. So Berger sort of hit on the problem. It's, the problem is not how to make ice in a warm world, but how to get rid of it in an unusually cold world. So it's like we're back here at the last glacial max. What caused all this ice to melt? Well, pole shifts can melt ice. If we look at the polar regions for previous locations in the North Pole, so this is these locations would be the Hudson Bay, the Greenland, and the Norwegian Sea. They actually pretty closely approximate the extent of the ice pack, estimated ice pack, at the time of the last glacial max. And the references for this, where this data come from, is in the paper. And what's interesting is that one can imagine that if over this period of time ice was accumulating, by the time you reach the LGM, it would be closely approximated by the union of these, or the union of these polar regions. And so what could cause the ice to melt is, now if this situation were at the North Pole and then suddenly shifted south, then all that ice would be shifted to a lower latitude where insolation is greater, and it would melt. So pole shifts can melt ice. It's sort of that nonlinear factor that I think is needed in these theories of climate change, but one that obviously climate scientists have been unwilling to consider. So, well, does this actually work out? Well, ice forms much more easily on land than it does on water, particularly salt water. So if you look at the land area at these hypothesized pole locations versus sea level, we find there's actually a correlation. So the amount of land, so if in fact the sea levels are dropping because ice is building up at these poles, that would be explainable or consistent with the amount of ice being formed, being in proportion to the land area at those poles. And it turns out that if we look at the sea level, which is again inversely related to the amount of land, there's a pretty good degree of correlation. It's 0.7 is considered a strong correlation. That's R squared value between land area at these hypothesized poles. So this is the current pole, the Bering Sea pole, the Greenland, the Norwegian Sea, and the Hudson Bay pole. So the Bering Sea pole was the pole just after the penultimate glacial max, as the current pole is the pole after the last glacial max. So these are very similar. So how do we get dates for these poles? Hapgood cites a lot of climate data. A colleague of mine, Mark Gaffney, did an analysis finding sources of mammal assemblage zone data in Britain, where basically these bone caves, so-called bone caves, contained evidence of different mammoths, different mammals at different periods of time, dated using stratigraphic information. And what the data reveal is, in one particular cave, Joint Mittner, there was evidence of, well, not evidence, there were fossil remains of hippopotamus and spotted hyena, which are tropical or subtropical mammals. In Bacon Hole, another bone cave, they had mammoth and vole fossils. At Banwell, fossils of polar animals, Arctic fox, reindeer, and at these other caves here, horses and again, woolly mammoth. What's interesting is that these different mammals here are correlated with these climate zones. And these climate zones here, if we look at the location of these caves, their latitude relative to these poles, notice how they track. So Banwell, let's go through it systematically. We start with the tropical, the earliest one, Bering Sea. The Joint Mittner cave was at 20 degrees latitude relative to the Bering Sea pole. So it was in the tropical zone. And then with the pole shift from Bering Sea to Greenland, it shifted to temperate, and so shifted to about 55 degrees, where these polar mammals are found at Banwell over this period of time, based again on our model, the North Pole being in the Norwegian Sea. This cave would have been at a latitude of about 75 degrees. So, very, in the polar region, and so forth, and then it later came out of the polar region as the pole shifted to Hudson Bay into the Arctic. So these correlations between latitude climate zone and these different mammal fossil remains, Mark Gaffney used to come up with the dating of these poles. So that sort of establishes the chronology here, which is again not inconsistent with Hapgood's work. It just sort of fleshes it out and refines it a little bit. What was interesting now is finding that if we look at, we put this up against the sea level changes, and now start looking at, okay, what else was going on in the world in terms of things like magnetic or geomagnetic events or volcanic events. It turns out there's been a number of what are called geomagnetic excursions. Excursions are shorter term reversals of the geomagnetic poles, or periods where they become unstable or they go to zero. But these last tens, hundreds, thousands of years, as opposed to millions of years that occur, much longer time frame with geomagnetic reversals. So these are sort of micro scale in time events. And these are four, I show here, Blake, Norway, Greenland, Lachamp, Mungo, and Gutenberg, 5 within the last, 120,000 years or so. Following these events, we have a number of supervolcanic eruptions. The Toba eruption, which is the largest one, I forget exact period of time, but it was an enormous VE8 volcanic explosivity index 8 event, one of the largest that is thought to have been responsible for mass extinctions. This closely follows the Greenland, Norway hypothesized pole shift. And notice that there's a change in sea level that takes place after this. Similarly, I glossed over the Blake. There isn't a known volcanic event after that, but there's also a fall off there. And we see similar ones occurring here, here, and here. So it appears that there might be some sort of connection between pole shifts and these other things that are taking place. So, to be cautious here, correlation, yes. Causation, maybe. Mechanism, who knows? We don't know. But the flow is something like, or the hypothesis is something like, a magnetic excursion or magnetic event occurs that results in a pole shift that then induces changes that cause supervolcanic eruptions that lead to glacial events, not just climate changes, but long-term events. So not just a bunch of smoke going up in the atmosphere or dust that later abates and the temperatures come back to normal, but something more permanent that occurs. So if we look at the Earth in a very simplified way in our magnetic field, the core field can be modeled like the magnetic lines from a simple dipole bar magnet emanating at the north and coming back in the south. Like the core field, the crust also has a field, called the continental ferromagnetism, and there's a north pole south pole pair shown here. And it's different from the core field. It's similar, but it's not exact. It's not completely correlated with it. So the mechanism that I suggest in the paper as a possible mechanism behind pole shifts is something like this: that normally the crust and the mantle are locked together. In other words, the core field shown here that we saw earlier, and the crustal field, the crustal ferromagnetic field, the lines or flux are in the same direction. So everything is locked together, and the crust, in effect, sticks magnetically to the mantle. Now, imagine a geomagnetic excursion occurs where the core field flips. So now it's going the opposite direction. In this case, now the crust isn't stuck to the mantle, but it could, hypothetically move, sort of like it could, in some sense, be floating to some degree over the mantle. Again, these are very preliminary qualitative ideas, but the basic mechanism is, is something that, presumably to some degree would occur if the field reversed. There would be a reduced, the friction between the crust and the mantle would be reversed or reduced. And under these conditions, it's possible that the crust could move more easily. So, where Hapgood was looking at the idea of the crust moving, the weight of the ice moving the crust, torquing it so much that it would move it over the mantle, as is, we're postulating a situation where the friction between the mantle and crust could be reduced. And if that were the case, and it could then move during these periods, then perhaps changes could take place under these situations. And then at a later time, when the core field reversed back to the normal direction, the crust would once again become locked to the mantle. And so that's just summarized in this cartoon. So what could actually cause this to happen? The mechanism I propose is the tidal forces. These are the forces that move Earth's oceans. And it's kind of interesting. After this paper came out in May, it was around the same time I noticed a reference, and another group of researchers had proposed the idea that plate tectonics actually might be driven by Earth, Sun, Moon tidal forces as well. And it's also been thought to be a factor in earthquakes, in certain types of earthquakes. So what I'm proposing here is that during periods of geomagnetic reversals, where the crust becomes unlocked from the mantle, the moon would pull on the crust just in the same way it pulls on the oceans. But obviously, being more massive, it would take place over a much longer period of time, much more gradually. So it wouldn't be an instantaneous event. But over time, with enough, given enough time, if the friction were reduced between the mantle and crust to a point to allow the forces to overcome that, then we could begin to see a movement of the crust by the moon. Now, this is sounding, perhaps a little far-fetched. Let me just take a step back, and because this has gotten it's a little speculative, but what we can do is create a simulation of what would happen using a model of the Earth's crust. It's a crust 1.0 model, that represents the thickness and density of the crust. And from that, we could actually compute the moments of inertia. So this is of the crust, not of the whole Earth, but just of the crust. And we can do it with and without ice. So we can look at the amount of ice pack at the time of the LGM and see, how that affects the moments of inertia. If we do that, we find without ice, we have what's called the theoretical axis, theoretical rotational axis, being located at a latitude of about 1 degree north and 18 plus degrees west. This is like practically on the equator. So that's without ice. With ice, it's about the same. It only changes about 20 kilometers. What's interesting is that this is not the theoretical axis rotation of the Earth. The rotational axis of the Earth is 90 degrees away. It's through roughly in the polar regions. This TRA, theoretical rotational axis, is near the equator. And so if we plot it, and these are the dotted lines of the zones of the tropics, we see it, it's very close to the equator. We could plot the TRAs relative to the other poles for Hudson Bay and the Norwegian Sea and Greenland and Bering Sea. And they all are roughly within the zone of the tropics. Now, what's interesting about this is the zone of the tropics is the direction within which tidal forces, act directly. This, the ecliptic, the line along which the moon and the sun and planets move, but we're concerned mainly with the sun and the moon. They're confined in this region. So this suggests that if they were at play, if they were torquing, creating tidal forces that were pulling on the Earth, they would act in this area, and their influence would be limited to this part of the Earth. So you wouldn't expect them to be able to jerk, the crust way up here or way down there. And in fact, that's sort of what we see here. So again, this data are very preliminary, but the intent is really to suggest a new direction in research, to at least suggest the possibility that we haven't really been looking. We haven't covered the bases. There are some other possibilities, and we shouldn't rule out crustal displacement theory. It still should be considered a possible phenomenon, and perhaps even, as I've shown here, a plausible explanation for climate change and the ice ages. So what I'm suggesting is, if this is the current theory of climate change, by adding in what we've talked about here, we don't know what causes geomagnetic excursions. There's a lot of speculation, a lot of theories, but if these do in fact unlock the crust, and then tidal forces are able to displace the crust, this could be the nonlinear factor that really, together with insulation, explains temperature, sea level, and polar ice. So, in summary, Hapgood's theory may be the missing link in not understanding long-term climate change, which is what Hapgood set out to do. But in my interest, what I started talking about up front was the rise and fall of past civilizations, and this was really the motivation behind how I got interested in it, and sort of what led me to try to figure it out. No one else, after having published these papers on the pole shift hypothesis and the shifted pole model and looking at archaeological sites, I was hoping someone would come along and come up with some new version of Hapgood's theory, Hapgood 2.0, which is what I called it. No one had. So in the meantime, this is my attempt to at least get the ball rolling, to the extent that an electrical engineer can do so. But I think the understanding, basically the correlations are there. Whether we actually have causation, and whether this can stand up to physical theories, physical models of more detailed models of the crust and magnetism and earth changes and so forth. Really, I leave that up to the experts. But in all humility, I offer this up as an attempt to get us out of what appears to be a dead end. We just don't seem to understand climate change, and we don't seem to understand how our civilization has gotten here. There are many enigmas that we're kind of stuck, and this is perhaps the new direction that we can move in. So I thank you for your time, and I look forward to your questions.
Thank you, Mark. I'm trying to see how we can make your screen full size here. There we go. I don't know how that happened. All right. Very interesting talk. And I'd like to remind our participants here that if you have questions, to please type them in the Q&A box, not in the chat window. And then we're going to start to address the questions here. We already have a couple. So if you're ready, we'll dive right in.
Good.
Okay, so this question actually came from a YouTube viewer who was watching this live stream on YouTube. Could you elaborate on the increase in tidal bulge at the equatorial regions during excursions?
So this is a question on this is more of a quantitative sort of question, and I don't know the answer to that. what I'm suggesting, not so much in terms of magnitudes, but sort of just general phenomenon that could occur. I think you're going to require, and I assume by tidal bulge, this would be a bulge of the crust. And you know, I don't have those models available. This is you know, again, I appeal to the geoscientists out there and the physicists that could, you know, write a finite element simulation and do these computations. It's sort of beyond what I'm able to do right now. So I do not know what the extent of that bulge would be. I would expect it's, you know, it's certainly going to be much smaller than you find, you know, the ocean's high low tide varies by a considerable degree. This would be much smaller, and again, as I indicated in the talk in the paper, the effect would be a much smaller force over a much longer period of time. So, given, you know, you could overcome that initial friction, you could move it slowly, ever so slowly, but over you know, enough time, there would be enough force. There's certainly enough energy there to do it. Whether or not it can overcome the frictional force, and that depends on the degree to which the magnetic reversal would reduce the friction between the crust and the mantle. And again, that is, these are ideas, but they're very qualitative at this point. So if the person that asked the question has any ideas, I'd be very interested to hear them.
Wonderful, thank you.
Okay.
All right, we got some more questions coming in, and again, reminding people to feel free to type them in or upvote the questions that you see in the window that you would especially like to see answered. Margaret Moga asks, my understanding is the geomagnetic excursions are relatively slow, but the pole axis shifts can happen quickly. Is this true? Well,
you know, I don't think anyone really knows. You know, there's if you look up Hapgood's theory, the Wikipedia entry comes up on catastrophic pole shift hypothesis, and you know, this in this hypothesis, it's generally assumed that this is something that happens very quickly. It's cataclysmic, causes floods and things of that sort, which you know, which tie into myth and legend. I mean, there may be that connection. Who knows? But I don't think we really know how quickly the poles, under these circumstances, could move. We do know that in the past, there's been some very large changes in the Earth's poles based on over millions of years using paleomagnetic data to basically track, you know, as evidence for these pole shifts. And so they occur very slowly over, you know, timescales of millions of years, suggesting something probably, you know, well, something obviously more quicker here on the order of maybe hundreds or thousands of years. You know, looking at, you know, the last 130,000 years, if there's been 5 pole shifts, you know, it's probably on the order of 100 or 1,000 years. It can't be much longer than that. But again, the time constant on that, it's going to have to do with the friction and the amount of force, and it's probably possible to calculate it, but I don't know the answer. Again, anyone that has anyone is interested in joining in on this research, I invite them and I encourage them, because it's you know, I think there are, like this crust 1.0 model that's available out there. This is something Einstein didn't have. You know, his calculations were back of the envelope. Now we can actually simulate and compute moments of inertia, and you can do a lot of hypothesizing and a lot of testing. So, you know, I think the data and the tools are there. I think people just have to do it, and people that have the expertise to take it, you know, to the next level. So thanks, Margaret, for your question.
Great. All right. Question from John McDonough. Could a gigantic Hall effect cause the volcanic eruptions after a geomagnetic quick change? Are they in the right place?
John, you know, I don't know about that. I was thinking of it more in terms of a geological, um, uh, sort of the effect of the crust moving over the mantle. There's these mantle plumes, and there's a lot of stuff going on under the crust that where under where volcanoes are, and in hot spots and so forth. And so if the crust does start moving and these faults start shifting, this could be a reason why in places where the crust is weaker, the magma comes up and creates new volcanoes or causes old ones to re-erupt. I don't know. Again, that's a little bit beyond my area of expertise. But if you have any ideas on how that could happen, again, I'd be very interested to hear what they might be.
Great. Let's see here. Pardon me. A question from one of the Facebook viewers. Has anyone considered that there may be two different types of tori, excuse me, in the Earth's magnetosphere, a traditional donut shape and another globe-shaped torus, which sits inside the donut torus? And it looks like there's some additional stuff from that same person. The globe-shaped torus could flip while the donut-shaped torus remains stable.
Yeah. This might be sort of a second order thing. I'm kind of looking at more sort of first order, back of the envelope mechanisms that establish plausibility. Our forces, within an order of magnitude, sufficient for things to happen without really thinking too much about the specifics about how they might happen. Could they potentially happen? So I'm deflecting a lot of these questions because these are really kind of outside the scope of what I've thought about and what's in the paper, but certainly things that would you'd want to be thinking about, but I haven't done so. Thank you.
Okay. Another question from one of our YouTube viewers. Was Britain sitting near the equator several thousand years ago? And can we tell how the land masses shifted as a whole or independently?
Thank you for that question. This is a question I can answer. So, my main area of interest here is the connection between pole shifts, previous locations of the North Pole, and previous, if you will, world ages. My hypothesis in the shifted pole hypothesis paper published in 2020 is that the sites that are built in alignment to these older poles were built tens of thousands of years ago. So a site like Baalbek in Jordan is not in Jordan, in Lebanon, is it's well known to be on ancient foundations, and based on this model could be 75 to 130,000 years old. So this is sort of the motivation for me. I teamed up with an environmentalist who was able to identify a lot of older papers and so getting to this question here, the paper that papers Mark found had to do with these mammal assemblage zones in Britain. And yes, so the short answer to this question is yes. About 130,000 years ago, the dated bones and these bone caves suggest that Britain was, in fact, within a subtropical zone. So that's probably 20, plus minus 20 degrees away from the equator. So not several thousand years ago, but 130,000 years ago. And this was the time when the North Pole, hypothesized, was in the Bering Sea. So at the North Pole, at that location, you go to Google Earth and you take your ruler tool, you'll find that Britain was about 70 degrees away from the Bering Sea at that time, thereby placing it in the subtropical zone. And so, yes, based on the animal data, that's and the dated and the dating that Mark used, the cave, that particular cave, Joint Mittner, is dated to be the fossils in that cave are dated to be 130,000 plus years ago. And so, yes, at that time, Britain was pretty close to the equator, a lot closer than it is now.
Thank you. I have a question that it isn't so much specifically about the details of a particular aspect of your talk, but a broader question that is always of interest to me on these talks. We're the Society for Scientific Exploration, and we often have speakers talking about things that are anomalous in terms of mainstream science. So I guess my question for you is, what, if any, response have you had from the mainstream scientists? You talk about interest in maybe encouraging geologists and geoscientists to take a look at this. Have you had any response, and if so, what is your primary critique of why they think this may not be an appropriate model?
Well, for the most part, it's been crickets. I'll be honest, but I have had a few emails through like ResearchGate, and I don't think anything's come through the Journal of Scientific Exploration that I'm aware of. But one physicist up in Canada pointed me to a paper that he had written a few years back, doing the mathematics of whether it was possible for an asteroid hitting Earth obliquely to displace the crust, and what the effect of that would be. So he actually did a first order back of the envelope, a little bit more detail than that. But looking at sort of what's the weight of the crust, how much force would be in this imparted by the asteroid, and how would it move? Would it move the crust? How far would it move it? How long? What would the time constants be? So this paper, and I don't have it at my fingertips. I probably should have grabbed it to cite it, but and it's not cited in my paper because I wasn't aware of it. Is exactly, I think, the next step that needs to be taken to sort of at least establish plausibility, right? That's all we can really do. Because these are like, kind of, when you're a generalist, there's the danger of oversimplifying. But if you're an expert in your particular area of expertise, you're generally not going to venture outside of that. So it's a challenging situation. So I think, like I said, I sort of put it out there as this is the first step in suggesting a direction to go. And I've had some, in answer to your question, Mark, I've had a little bit of feedback, nothing negative, because at the end of the paper, I really do say, hey, look, I know there's been a number of problems with this. Let's go through them, and and I think they can be pretty much discounted, unless you're a diehard. If you're a diehard skeptic, you're always going to find something. But if you're open-minded, I think there's enough here to say, hey, look, there might actually be a possibility, and let's see if we can take it a step further. So it's kind of where I feel, I'm at right now.
Well, and you're not, I mean, at least as you've presented it here, you're trying to hypothesize potential mechanisms. You're not necessarily proposing that to invalidate existing, not that Einstein is wrong kind of a thing here, right? You're trying to find existing mechanisms that would be consistent with known models in science, that you're just trying to put them together in ways that might explain these data, at least as I'm seeing what you're talking about.
Well, like, in the appendix of the paper, I actually compute the moments of inertia with and without ice. I alluded to that in the talk. Mm-hmm. And the math and all the details on how I did that, and it's a standard model that's used, and so I did the finite element calculations and so forth, and actually what I was able to show is that the effect of the ice is very small, and so it really does validate Einstein's his feelings at the time, which were, I'm sure he had, he knew roughly what the mass of the Earth was and how much ice would be involved, and he obviously did his calculations. And so, I think using a little bit more detailed model and running the calculation through, finding only a 20 kilometer shift in the theoretical rotational axis sort of says, yeah, Einstein was right. However, he was talking about the crust being locked to the mantle, floating on this plastic sort of layer between the hard crust and the molten core. And what I'm proposing here is that by with the geomagnetic reversal and having this magnetic flip, it might actually, by reducing the friction, it's actually changing the rules of the game a little bit. And so it's a different problem than Einstein was thinking about. It's the crossover on a very slippery mantle. And so, okay, so now what are the calculations now? And forget about the ice. Let's think about the moon now, because the moon obviously has an effect on the tides. And I mean, it's remarkable the extent to which the moon moves water on this planet. So why not the crust? If it could move, why not the crust? So I think these are all within the realm of possibility, under the right, the right conditions.
Sure. All right, I'd like to invite, we have about 3 more minutes left. I see no more questions in the Q&A. If someone has a question that's burning, please type it in quickly here and we'll ask Mark to answer it. And we'll give another 30 seconds or so before to see if anyone has any additional questions. And then at the end of this session, when we end the session, then we'll be going back out into the social lounge. And will you be able to join one of the tables so that people can have a face-to-face conversation with you then?
Sure, happy to. Thank you. Yeah.
Wonderful. Thank you. All right. Well, I'm not seeing any other questions. So with that, I'd like to thank you very much for a very interesting talk. And we'll end the session. And I see several people are applauding virtually, and we'll allow them to talk to you in person. Thank you so much, Mark.
Thanks very much.